Hello again, we meet again I guess. So we were discussing the concepts related to equilibrium in our last class, right. So first we will talk about or review those aspects and then take a holistic view of what we have discussed so far, because now we are going to move on to another major topic or one of the other fundamentals that we are going to discuss about, and which is the kinetics, right. So first let us look at what we have discussed in yesterday's class for now I guess, yes. So I believe we were trying to solve, right, we are trying to solve for systems at equilibrium, right. I mean I wanted to know what are the concentrations of various compounds at equilibrium and what are the equations that I can use. I can use mass balance if applicable or depending on the scenario. I can also use charge balance, right. More or less what does this mean? The concentration equivalents of all the cations will be equal to the concentration equivalents of all the anions, right. But rarely will you have a complete or comprehensive knowledge about all the cations and the anions. So this has limited applications I guess, but in general charge balance is always followed, right. And then we obviously looked at equilibrium equations, but as we noticed in the last few classes or couple of classes anyway, we are still missing a few equations to be able to solve for our unknowns. So what is this set of equations I guess? So in this particular context we introduced a component balance, right. So what does that mean I guess? We are going to introduce a concept of a building block, so this can be hypothetical, can be, need not be though, right. And what do we end up doing I guess? Let us review the process. So we look at or list the species, and what are species? These are the actual compounds that exist in the solution at equilibrium, right. And depending upon the species, so let us take an example I guess. Here let us take CH3COOH dissociating into its conjugate base, right. It dissociates by giving out its proton here. So I will approximate this by saying HAC, acetic acid, state ion and H plus, right. So what are the species here? We know that we will have HAC and AC minus, and we will also have H plus. Whenever we have H plus we will also have OH minus. Obviously water is always a species, but we are not going to list that I guess, right. And what next? So we need to choose components. And how do we choose these components? We choose them such that the minimum possible number or combination would be able to give us all the relevant species. So thumb rules, we always choose H plus, or we try to rather, and choose the most deprotonated form of the particular acid, and which in this case is the acetate ion, right. And then I believe we said for formation equations. So I am going to skip that for now, right. How are you going to form the relevant species from the various components? And then from the formation equations you will be able to write the tableau or come up with the tableau. And what is this tableau about? It gives us an idea about the component balance. So here we are going to do that I guess, H plus and AC minus, the components there, and all the species here HAC, AC minus, H plus and OH minus, right. How many H plus do I need to form HAC? 1, 0, 1 and minus 1. And why is OH minus negative minus H plus? Because it is H2O minus H plus is equal to OH minus, right. So again AC minus 1, 1, 0 and 0, and if I know based on what it is or what is the initial solution that is leading to or the source of all these components, we can equate that here. So next up I will need to write my equilibrium equations, right. And in this case, I guess we have two equilibrium equations. One is the acid dissociation constant here, Ka1 equal to activity of Ac minus or state ion into activity of H plus, right, by activity of HAC. So this is the acid dissociation constant. Anyway, we are going to discuss this in greater detail later on, but for now please bear with me. So obviously we can, in dilute solutions, we can approximate this by the concentrations or relevant concentrations, right. So activities, we are now approximating them by the concentrations, right. And the other one would be the water dissociation, H plus and OH minus by activity of H2O, and obviously activity of H2O is going to be 1, and I am going to approximate them by the concentrations. Right, but still we have only two equations here, right, Ka1, Ka2, the equilibrium equations, and we have 4 unknowns here as you see in the species, right. So what do we need to do? We need to come up with two additional equations. What are those though, right? And that you will use the component balance. So if you look at this, I am going to balance the components, and whatever the transformations within the system or between the species, the total components are going to stay the same. So that is the concept here with respect to component balance. So H total equal to what now? Concentration of HAC plus concentration of H plus minus concentration of OH minus, right. And what about estate total? Total estate, I guess. So estate here looks like is only going to be either in HAC or AC minus, and if you know what the source of these compounds is, you can have that here, and you have now two additional equations. So you have 4 equations, 4 unknowns, and you can solve for that accordingly, right. So with this particular aspect of component balance, we can now calculate what are the equilibrium concentrations of any compounds, let us say, right, given the relevant conditions. So this always works. So out there, either from different instructors or from, let us say, nowadays internet is I guess popular with people, right. But anyway, so there might be multiple ways out there to solve various problems, but one aspect or one way anyway that would never fail is the component balance equation, a generic approach that always works, right. And here we are going to use that throughout the class. That is the fundamental here, or the building block here for our class, I guess, right. So we are done with equilibrium for now. So we are going to move on to the next major topic, which is kinetics, but we are very briefly going to talk about or look at what we have discussed so far in the class, right. So I am going to look at equilibrium now, right. So again we divide our class into equilibrium and kinetics, right. And then we are at the later stage of our classes going to look at the applications of these two aspects, with respect to the most commonly used or reactions, or most commonly what do we say, the reactions that we come across as environmental engineers in general. So acid base, and then complex formation or complexes, let us say formation of complexes, precipitation and dissolution, and more importantly the redox reactions, the oxidation and reduction reactions, right. So this is what we have for the later part of the class. So thus far we have been talking about the fundamentals here related to the equilibrium, right. So what have we discussed thus far? Let us say, I believe we mentioned that it is driven by thermodynamics, right, and thermodynamics again we need to look at the delta G values, that is equal to delta H minus T delta S, and then we looked at feasibility of this particular or a particular reaction, right. When it is negative we see that it is feasible, when it is positive not feasible or the reverse reaction is feasible, and when it is 0 it is at equilibrium. So obviously for visualization purposes we looked at state G1 and state G2. So higher energy state, right, so it can fall down the ladder to G2, and delta G here is G2 minus G1, and as you can see that here that is negative, and that can go through though. But if it is inverse though, obviously it is going to be not feasible there. For example, if it is G2 and G1, G1 can't move up the ladder to G1, so this won't happen, but G2 can fall down the ladder to G1, right. Again that is what we say when delta G is positive. Anyway, and then we looked at how enthalpy affects delta G, how entropy or degree of disorder affects the Gibbs change in Gibbs energy and so on, right. And then I believe we looked at the concept of chemical potential for a particular compound, and that is equal to the molar Gibbs energy of the compound. So chemical potential, what is that? I guess a potential for gives us an idea, right, about the potential for a compound to react. Chemical potential, it's similar to saying potential of a particular person or a particular company or such here, I guess, right. I am just drawing natural or simpler corollaries here, right, chemical potential here. So greater the potential, the greater the chemical potential, greater the potential for the compound to react and then fall down to a lower chemical potential. Yes, that is something we came across there. And then I believe we applied the what do we say, G systems, or came across calculating the Gibbs energy of system, and I believe what did we have there? So Ni mu I, Ni is the number of moles of particular compound or component, mu I is the chemical potential of that particular component. Also that is similar obviously to Ni Gi bar, summation of Ni and Gi bar product, I guess, right. And so then we looked at applying that to reactions, and I believe we looked at what is the change going to be and so on, and I believe we came across for a generic reaction Vi mu I of the products minus of the reactants. This is what we came across, and obviously what is this particular set of variables here, I guess, or variable here or the differential here. So how does the Gibbs energy of the system change with a small change in the reaction, or when the reaction has gone through a small extent, let us say. So that is nothing but obviously delta G, right. So obviously when we drew the particular figure here and we looked at one particular schematic, this is the G of the system. So when the slope or this particular variable dG by dx is negative, we see that the reaction is feasible, as in it can fall down from a higher energy state to a lower energy state, right. So anyway, the slope is going to be negative here, and when it is equal to 0, when the slope is equal to 0, we see that it is at equilibrium, and again when it is positive, we see that it can't move up the ladder, so not feasible here, not feasible, feasible here, and so on. And I believe this is what we looked at. And what else did we look at, I guess? Then we started looking at how to calculate delta G values at, I believe, standard conditions and then non-standard conditions, right. So standard conditions, we defined them as temperature equal to 25 degrees centigrade, and what else please, pressure equal to 1 bar, and we came across a new what we say term called the activity of the compound or component, and we said activity should be equal to 1 if it is at standard conditions, right. Activity, I guess at that time we were approximating it by concentration, right, and it gives us an idea about the ability of the particular compound to react, right. And so we came across this, and I think we mentioned that you look at the elements leading to formation of particular compound, right, and then we define the Gibbs energy of formation of these elements as equal to 0. This is our reference. So from that we can come up with or measure the Gibbs energy of formation of the compounds at standard state. We can measure this, right, and with these you can come up with any other reactions or delta G values for any other reactions that you want to, and this is what we looked at in that particular standard conditions, right. And then we looked at standard conditions as in what would happen to the system, or how would the system change with respect to the delta G calculations and such if the activity is not equal to 1, which is what you would observe if it is not equal to 1, or if temperature is not equal to 25 degrees centigrade and pressure is not equal to 1 bar, right. This is what we looked at. So with respect to activity not equal to 1, there were two aspects. One is the reactants themselves, and the other is the non-reactants. So in general we mentioned that two molecules, they collide, right, and then the reaction takes place. So the higher the number of what do we say, the reactants or the concentration of the reactants, the greater the possibility for collision, and thus the greater the feasibility of the reaction. Again, when you have charged species, which is what you would see or expect in your solution, or you have multiple non-reactants that are charged, and if the ionic strength is high, that can have a detrimental effect on the interactions between the two relevant compounds, or 3 or 4, right. So that is why we looked at activity, I guess, right. And what did we define activity as? Activity of a particular component or compound is equal to its activity coefficient times the normalized what do we say, what is this now, the dimensionless concentration of that particular compound, I guess, right. So for that particular aspect we will have different particular equations for activity coefficient. Almost all of them are function of I and charge. What is I? I is the ionic strength, right, and higher the ionic strength the lower the gamma I, and thus the lower the activity of the particular compound. That is obvious, I guess. The higher the concentration of the non-reactants that are going to interfere with your reactants, let us say, the lower is going to be their ability to react, let us say. So that is what we have here, that was the take home message there, right. And obviously again we define how to, what are the units we need to look at with respect to the concentration of I here, and I believe for aqueous phase we said we need to use molal, right, not molar here, and if you use molar there will be an error of what I think 3% here in this case. So aqueous phase, and then gaseous phase we said it is going to be what now, partial pressure, and in the liquid phase and in the solid phase it is going to be mole fraction of that particular component. So that is how we define that, right. So what does this mean, as in if I have a equilibrium coefficient equal to activity of this thing, and so on, right, and I need to write down the concentrations here, what am I going to do? If I have an aqueous phase here, I am going to use molal concentration. If I have a gaseous component here, I am going to use a partial pressure here, right. So that is what more or less it translates into. And then we started looking at what are the effects of temperature not being equal to 25 degrees centigrade, right. I think we looked at the Van Hoff equation, and I think we looked at the relevant aspects. In general, right, for especially with respect to the exothermic reaction, this is what we looked at, I guess, the example. We are not going to go into that in detail now. In general, the greater the what do we say, temperature, the greater the kinetic energy of the molecules, and greater the chances for collision and chances for the reaction going through. That is in the general case, but we looked at the relevant equation for kT by kT naught for the relevant scenarios, and we looked at them, right. And then we also looked at what would be the case when pressure is not equal to 1 bar or the standard conditions, and then we looked at the relevant aspects again, K at P pressure and K at the P naught standard and how that varies. And in general you know that, let us say if this is the current pressure of 1 bar, and let us say now you are applying twice the pressure, let us say, right. So this is going to resist, or the higher the pressure, the greater the resistance to change in volume, right. So whenever the delta V needs to increase, so if you are increasing the pressure, that will be to the detriment of your reaction, because you obviously need, not detriment I guess, the equilibrium coefficient is going to shift towards the left, yes, and this is what we discussed in the class. So again we are not going to go into that in greater detail, right. So I believe the last aspect then we end up covering, I believe, was looking at the component balance, I believe, right. And before that we also looked at phase equilibrium, right. So a particular compound, let us say compound A, if it is in particular phase 1 as in gaseous or liquid and gas, right, it will equilibrate between these two phases now. So 1 mole in gas and 2 moles in liquid and so on, and so we came up with relevant relationships, and I think one for this particular case is the Henry's constant, right, that gives us the relationship between concentration in the gaseous phase and concentration in the liquid phase, or in general the aqueous phase here, I guess, right. And keep in mind that the units of Henry's constant can be different. So actually if someone defines the units in a different way, you can even have an inverse of this particular fraction here, right. So you just need to look at the units before you come up with your particular term, or look at your particular units of your particular individual variables here, right. So it can be atmosphere per mole, or moles per what do we say, liter, right. This is one particular combination of units for Henry's constant, and there can be multiple other equations. So same case we looked at gas, liquid, and fluid and solid what do we say, phase equilibriums, and we looked at how it goes about and such, right, and we looked at a generic example, and then we came across the component balance which we discussed today, right. So anyway, now we are going to move on to the next major topic, which is the kinetics, right. And kinetics, what does that give an idea about? I guess it gives us an idea about how fast is the process or the chemical process, right, how fast is it. and as we talked about, it is a characteristic. It is not a state, obviously, it is a characteristic of your particular process. So, right, usually we apply them to reactions at a micro scale. And why do you need information about kinetics, let us say, right? For example, let us say you have an activated sludge process here. I mean, I'm poor, what do we say, very poor with respect to drawing figures here, so you should excuse me, I guess, right? So, let us say you have an activated sludge process here, right, and with the return here and so on, and this is where you have your reactions occurring here, let us say. So, let us say you want to, you conducted the test in your lab, let us say, right, and you want to obviously scale this up. So, what do you need to look at though? You need to look at the relevant kinetics, right, the kinetics of a particular compound. Let us say now most people are looking at emerging contaminants, or let us say talk about a pharmaceutical compound, let us say, right, a pharmaceutical compound that is entering here, and you want to see how fast or if any is your particular compound being degraded in your activated sludge process, right. So, you will conduct the relevant lab tests, after regression you will come up with the kinetics, and then you can use that to scale up your particular model later on, right, and apply that to your engineered systems too, yes. So, with respect to terminology, we usually come across rate of a reaction, right, and we in general we will use two aspects or mostly one, but we will discuss two here: overall rate and volumetric rate, right. And overall rate, as it indicates, I guess, is just amount of the substance degraded or formed per time, or change in amount of that particular compound per time, right. But here, you know, let us say if we apply this to this ASP, let us say, we are not talking about with respect to particular volume though, right, but that is going to create issues if not in ASP. Let us say if you have a river, let us say, right, you are dumping a compound here, the river is flowing in this direction, right. Let me draw a better figure here, right. So, we have a river flowing through, right, and let us say at Haridwar somebody is dumping industrial waste, and I am at Roorkee here, and I want to see the effects of this particular compound here by when it reaches me at Roorkee, right. So, for here though, as we see, the reactions are occurring throughout the course of the river. You will have, what do we say, obviously the transport mechanisms, advection and what do we say, diffusion, but obviously you are going to have either rate of formation or loss of your compound, probably loss, and I want to be able to look at that. So, if I look at the overall rate, that will give me a misleading picture or incomplete picture, right. So, what do I usually go for? I go for a volumetric rate, and that is nothing but change in amount of your substance per volume per time, right. So, that is what you would see here. So, in general this is what we are going to use, volumetric rate throughout the course of our class, yes, and that is amount of your substance that is transformed per volume of your particular system per time, let us say, right. And in general next aspect is going to be the sequential reactions. So, let us say if I have a compound A in solution, right, it can transform into multiple ways, right, in the real world. It can either go or degrade through parallel reactions to B and C, right. Here A and A going to B and A going to C are parallel reactions, right. So, here you can have parallel reactions. At the same time you can have a series of reactions, right. So, we are going to discuss these two aspects in greater detail and why. So, for example, let us say if I am now looking at this particular case with respect to what do we say, A degrading via two reactions, and those two are parallel reactions, A going to B and A going to C are parallel reactions. So, let us say if you want to model this, right, and you are going to look at, let us say for example, you know that A going to B is remarkably faster than A going to C, you know, let us say 1000 times faster in magnitude, let us say, if the rate constant. We are going to talk about what rate constant is later on. For now, think of it as a metric that will give us an idea about how fast the reaction is or about the kinetics of the reaction. So, again we are talking about a new term, it is a rate constant, and this is a small k, I guess, right, a rate constant. So, let us say rate constant of A going to B, K1 is far greater than A going to C, right. So then I can neglect A going to C and just say it is just A going to B, right, to simplify my set of process. And then the next aspect is going to be the series reactions, right, when A goes to D goes to E, right. And in this case, let us say, what am I concerned with? For example, think of this, let us say, as I go from, let us say, Roorkee to Delhi, let us say, right, and assuming that, you know, this is a hypothetical case in India, I guess, right, that free of traffic, a nice what do we say highways here, right. What do I need to look at though? I need to look at where I have the major population clusters. Let us say I think I come across Modi Nagar and Ghaziabad, and at this particular point in space, right, I am going to be stuck in traffic half an hour or 1 hour, right. So if I am looking at the rate of my particular travel from Roorkee to Delhi, what defines my in general travel now, right, at that particular point in time, or the rate limiting step, right. So this is a new term that we have in your series reactions. You have a rate limiting step. And the analogy we are looking at is I travel from Roorkee to Delhi, I hit traffic in Ghaziabad or Modi Nagar, and here the traffic piles up here for many what do we say kilometers or so, right. So here, irrespective of the rate at which I come here or here, the crucial aspect that I am concerned with is the rate at this particular point in space. So similarly in reactions, let us say I can have A going to B, going to C, going to D, and so on, but if let us say C or B going to C is very slow, you are going to have a lot of accumulation of compound B, right. So you can say that A going to B goes to C, why D, I guess. Why is that? Because B to C and then pardon me, C to D is a fast reaction, let us say. So I can approximate this particular series reaction by saying it's A goes to B goes to D. So in general, the rate limiting step is when you have accumulation of that particular compound or the reactant, you will observe accumulation of your reactant, right, that is the rate limiting step here. And in this case, the reactant here is going to be B, as that is accumulating because B going to C is very slow, right. That is what of your reactant. Think of that as accumulating at that particular traffic jam or junction here in your travel case, I guess, right. So I believe I have a set of what do we say graphs to look at, but I believe we are running out of time. So we will discuss this in next class, and for that for today's session, that is it from me, I guess.